So next we have Adam Malyali, who's a postdoc at Max Planck Institute, Berkeley. Will tell us about eROSITA's tidal disruption event calculation.
Yes, yeah, thank you. So I wasn't too sure what to present, so I tried to cover everything, which might be too much. But I thought it would cover as many bases of interest in the audience as possible. Yes, as Ricky mentioned on Monday, just some basics of eROSITA, but I'll just recap them quickly. So eROSITA's first 4 years were dedicated towards performing 8 successive all-sky surveys. So it was effectively rotating about its axis and orbiting around L2, and over the course of the 6 months, we basically scanned the entire sky. And during this time, it would detect about 4 million X-ray point sources every 6 months. And of course, if you're continually scanning over the whole sky over and over again, then you're going to have excellent insight into the transient X-ray sky. And then just to highlight, eROSITA was placed in safe mode in 2022. This was after the Russian invasion of Ukraine, because it's a joint Russian-German mission. So for time domain astronomy, then what we get with eROSITA, so if you have a source which is scanned, visited 4 times in each all-sky survey, then each plot here is the light curve from within 1 scan. And so the shortest timescales you probe are over 40 seconds. So that's the visit of the source in 1 eRO day. And then 4 hours later, then eROSITA scans over the source again. And then typically this happens about 6 times within 1 all-sky survey. So then you sample variability over 1 day timescales. And then 180 days later, then you sample the X-ray variability again. And over longer timescales, and you have a 2-year sampling of the X-ray light curve. And then, of course, on top of this, then you can do cross comparisons with eROSITA with previous X-ray missions. So for TDEs, then eROSITA is excellent at discovering them. So it has excellent soft response, localization of point sources to a few arcseconds. But the drawback is that we have sparse line curve sampling. And so it's excellent for discovering the systems, but if we want to infer more about the properties of each system, then you have to trigger a multi-wavelength follow-up. So if you've got, for the majority of the sources, we've only got sparsely sampled light curve, and we have to use that for population studies. So briefly on the eROSITA's TDE population. The way you do this, you obviously have a scan, and then you have a second scan, and then in some of these scans, then you'll have your X-ray transients popping up. And, if you do a cross match between the 2 scans, then these X-ray transients will pop out. And this is work currently led by our PhD student in the group, Yulia Krotova. And so you do a cross match. Well, currently she's selecting them in the first 2 scans. So the idea, you cross match the 2 source catalogs, look for sources which show significant variability between the 2 scans, and then select these as your X-ray transient sample. Obviously, not every X-ray transient will be a nuclear transient, so transient associated to the center of a galaxy. So you then have to filter down these X-ray transients into your TDE candidates. So there's basically a cross match done between your X-ray catalog and your optical catalog of galaxies and stars, and then apply a series of cuts based upon the multi-wavelength counterpart. So, for example, you exclude sources within the galactic plane, or exclude sources with significant parallax, and then exclude sources where the mid-infrared color suggests that they're an AGN. And then, of course, you look at the archival X-ray data from each source and make sure that there wasn't significant X-ray variability suggesting an AGN in the past. Yeah, and then after that, then you whittle it down towards a sample of things which look more like TDEs in the X-rays. Look at your light curves, do a spectral modeling, so look preferentially for softer X-ray sources, and also look at the optical data that's available. So just as an example of what Yulia is doing is she splits up the sample of nuclear transients into sources based upon their X-ray variability. So this first data point here would be your first ERAS scan, then second ERAS scan, third, fourth, fifth. And when she does this in selecting only systems within ERAS-1 and ERAS-2, which is about 300 nuclear transients, she then applies just the distribution of the whole sky. She then applies a series of like stringent cuts on what you think is a TDE. So if you say, okay, I'm only selecting sources with photon indices greater than 3, with a single decline in the light curve, like this. So this is the first ERAS scan, second, third, fourth. You see a large amplitude flare between these two scans. Then she can define a sample of golden TDEs. So it's obviously difficult to say what is a TDE and what is not. But if you effectively say the sources which show like a short-lived X-ray flare, and she gets down to a sample of about 25 TDEs from 1 year of eROSITA observations. So this is still work ongoing, so I can't go into too much detail on this. So at the moment, there's only 10 of these with spectroscopic redshift. So before going on to doing the population studies, you need to fill in this sample. I guess Suvi as well mentioned earlier that TDE or not TDE. And this is kind of quite well highlighted by this transient that we found fairly early on within eROSITA's survey. And so this is a double-peaked optical light curve. So you have this relatively large amplitude optical flare. And when an optical spectrum was taken off this first peak, then the spectrum just showed broad Balmer emission lines. And then there was a late time optical brightening about a year on. And this is when eROSITA first observed the system. So eROSITA observed a X-ray flare by a factor of about 600 or so, relative to an XMM 3 sigma upper limit. And yeah, from the X-ray side of things, then the spectrum is ultra soft, like other TDE candidates. But then obviously in the optical, you've got this extremely strongly double-peaked optical light curve. And also when we obtained the optical spectrum of the source at the second optical peak, then you have the formation of the transient Bowen emission lines. And so if you look at only the X-ray properties and the optical spectroscopic evolution, then you'd say this is a TDE. But obviously there's something more complicated going on in the system. And after we published this paper, then there was another follow-up paper where they said that the first optical peak was associated with emission released from the debris streams, self-intersecting and shocking and releasing the optical emission. And then the second peak here was associated with the delayed accretion onto the black hole. So we just basically showed this to show how difficult it can be to say that given X-ray transient is actually a TDE. One thing that we have seen so far is that the majority of eROSITA-selected TDEs are optically dim. So the majority, about 70 to 90%, either show extremely faint optical flares or no transient optical emission. And as a result of this, when you have your TDE candidate that you select with eROSITA and you obtain a follow-up optical spectrum, then typically we don't see the transient optical emission features that you see for optically selected TDEs. And so as a result, you can't necessarily rely on spectroscopic classification techniques that you've developed for optical surveys for these eROSITA selected TDEs. So effectively with eROSITA, we just see an X-ray flare, and then you don't really see a response in the optical. As an example of this, then this was one of the systems that we found earlier this year, or last year actually. And so in the middle bottom panel here, you have the optical light curve. In the top, you have the eROSITA detection. And so this TDE here was actually missed out from the ZTF sample of optically selected TDEs. And so it kind of shows how eROSITA is actually going to be complementary to the ZTF and, well, optically selected TDEs. With the system, it's interesting because the peak observed optical emission is the faintest of all optically selected or optically bright TDEs observed to date. So if you look at this y-axis here is the peak observed G-band magnitude, and you see that it's fainter than all of the TDEs selected so far. And there's also been a trend that the fainter optically selected TDEs decline over faster timescales, but this system goes over much slower timescales in comparison. And yeah, here's just a comparison with the other ZTF selected TDEs in blue. Interestingly as well, this system was located in a smaller galaxy, 5.4 arc seconds off from the center of a larger galaxy. And so it's about 4 kiloparsecs projectors offset. And so if you had similar TDE candidates where you've got a less good contrast between the two optical hosts, then such a TDE would also appear off nuclear. So this will be interesting to look for in next generation optical surveys. One of the other things that we found more recently, so I guess we all know X-ray bright TDEs don't necessarily show strong optical emission, and optical TDEs don't show strong X-ray emission. And there've been some mentions of viewing angle dependence. And what we found in this TDE is effectively an early time X-ray transient. So we scanned over this position, this TDE, and in the top panel here, you have the eROSITA detection here. And you see that this actually occurred 1 day before the first detection in optical. And after this eROSITA detection, then you have the optical brightening. And then we obtained a follow-up XMM observation 19 days later, and the X-ray flux had dropped by a factor of about 36. Whoa. We then obtained a series of optical spectra. So these span from 5 days before optical peak all the way through to 140 days before optical peak. And in the spectrum obtained 5 days before optical peak, then you have the formation of the He2 emission complex. And so this drives the spectroscopic classification of the system as a TDE. And then on top of this, so there's basically 3 key observed signatures. So there's the early time ultrasoft X-ray transient. You've got your, in the optical spectrum, you also have blue shifted H alpha. So the centroid's shifted by about 1600 kilometers per second. And then on top of this, we also have ATCA detection of radio transient emission about 20 days after optical peak. So it's just this set of red stars here. And effectively what we have in the system is a set of signatures which point to an outflow being launched at relatively early stages in the system. And so what we think is happening is that if you look onto a TDE early enough, then you might be able to detect the early X-ray emission from the early time fallback material onto the disk. And so if you have like some sort of collision-induced outflow from the streams self-intersecting, this then expands over time, and the material along your line of sight effectively becomes more and more optically thick over time. So that when we follow up the system with X-rays at later times, we don't see the X-ray emissions from the disk. So this is just an ongoing work in progress.
Sorry, are you saying the X-rays early on are from synchrotron?
No. So the X-rays at early time are ultrasoft, and so these are what we think are from the early time fallback material, or the material which has circularized at early times. And so you're getting a weak X-ray emission from this nascent disk, and then yeah, over time, then the amount of debris along your line of sight increases in density, and so your line of sight towards the TDE gets blocked by this material. And so, of course, if this mechanism is operating in other TDEs, then this would explain why so many TDEs that we're seeing are X-ray faint when we're following them up. So it's not only a viewing angle dependence, but also a time dependence for these systems. Okay, so some more info on some repeating TDE flares that we found. So this system here was effectively first discovered as a eROSITA-selected TD back in 1993, I think. So there was a large amplitude soft X-ray flare from a quiescent host galaxy at redshift 0.052. And the spectrum was ultra soft. Then the system was observed multiple times. I would say, for example, with Swift XRT, XMM slew, and also with eROSITA. And nothing was detected in the first 4 scans with eROSITA. And then in the 5th scan, then we observed a large amplitude X-ray outburst again. And so you have a rebrightening to a similar luminosity as what was observed with eROSITA. And interestingly, we also observed a large amplitudes cutoff in the X-ray flux again. So we triggered XMM observation of the system, expecting it to potentially be another TDE candidate. And the system was effectively non-detected. And still 200 days later, the system was non-detected again. The rise and decay timescales are also much shorter than what we see in a normal TDE. So the rise timescale comes from the eROSITA observation. So you have to assume a self-similar evolution between the 2 outbursts. And then with eROSITA, you can also place constraints on the decay timescale based upon how deep XMM observation obtained shortly after the eROSITA detection. And importantly, this system did not show transient optical, UV, or radio emission. So this is a class of X-ray transient, which, if related to partial TDEs, was just not detectable by optical surveys. And also, it's interesting that this system is potentially an intermediate between your QPEs and also your TDEs. To go back to the origin, then we think it's also likely to be a partial TDE, where the star has survived an initial encounter and then has undergone a second return to pericenter, another return to pericenter and been disrupted again. And so even though the recurrence time scale here is about 30 years, it's likely that it's actually a shorter recurrence time scale, but we've just missed the bursts in between. Because it would be super unlikely for us to have been observing the system at the right time. If it is a 30-year recurrence time scale.
You said there, go ahead, Ed.
Is there an attempt to monitor this in some logarithmic way now or something?
Yeah, the big challenge with this is that it's a short-lived X-ray flare. And we monitored it for maybe 2 or 3 months after the eROSITA detection on a weekly basis. And then we didn't find any significant detection. So it's very difficult to justify to Swift team, for example. Please give us time to look at it. It'd be amazing if we could, but it's quite difficult to.
Did you say it was intermediate between a QPE and a TDE?
Yeah, at least with respect to the rise and decay timescales. So it's obviously much longer than the duration of QPE outburst.
Could it be a QPE?
Depends what QPE is.
Yeah, I mean, based on like some of the papers, can that be? Could it be a QPE that's separated by several weeks, right? In principle, like the one I showed, where they're 20 days apart.
Yeah, well, I mean, if you say that's a QPE, then yes. But then I guess it depends on the models. I guess at the moment we don't know what a QPE actually definitely is, and so we don't know if there's different classes of physical mechanism operating.
Well, they're periodic eruptions. Forget the models. Anything that repeats.
Well, yeah, then that's repeated.
Yeah, so maybe it's a QPE. You just have to monitor it to find the period, perhaps.
Yeah, but then it could also just be a repeating partial TDE. And then it just depends upon what you call. It's just the name, isn't it?
I think maybe you're talking about this in the next slide, but if it was a repeating TDE, you could put rough estimates on the repeating time scale based if you think that because the things that will determine how short it possibly could be are the fallback time scale, or is a fallback time scale, which is then affected by the eccentricity as well in a case where you have a bound disruption. And so there's but it's going to be the black hole mass and the eccentricity. So you could say, okay, given the black hole mass from galaxy scaling relations, and the time scale we get in this repeater, what is the range of expected repeating time scales? I mean, it would be hand wavy given the data, but it'd be better than nothing.
Yeah. Yeah, that's a good point.
You can talk.
It could also be a new TDE, right, in the same galaxy, 20 years.
I think that's unlikely because
I think the likelihood is, I mean, it's unlikely to get,
If it's a binary black hole in there, then the likelihood is like once a decade is the estimate, so.
yeah, but then you have the problem that there's not really any other evidence for the binary black hole evolution. Because you'd expect longer fallback timescales, etc.
you'd also expect a lot more repeated TDEs and binary black holes, which we'll talk about it tomorrow, so.
Yeah, so
But then it wouldn't, yeah. necessarily.
And so then just to briefly touch on partial TDs, there's quite a nice paper from Tejo Rio earlier last year where they look at the spread in the specific energy distribution. And so this is like effectively like the distribution of the specific energy in the debris. And you effectively find very different spreads depending upon whether you have a severe partial TD or a weak partial TD. And yeah, so it's for weak partial TDs, and you can have much steeper fallback timescales or slopes in the fallback timescales. Yeah, and so you can have, there's potentially like a very widespread of observed behaviors of TDs depending upon configuration of the system. So lastly, then I'll just touch on probably the most extreme system that we have discovered so far. And so this was work led by Zhu, MPU, who's also a postdoc. And this system was initially discovered as a TDE candidate. So the system wasn't discovered in eROS-1 here. And then the system was detected as a faint soft source in eROS-2, which then brightened 6 months later. And then was also brightened and hard in eROS-4. This system is associated to a quiescent host galaxy, which has not shown any signs of AGN activity in the optical spectrum when we followed it up. And so here's the light curve for the system. So this data point here is the first detection with eROSITA. And so this is in this state, the system was ultra soft. And then the second eROSITA detection was 6 months later here, and the system had hardened. After this, then of course we were super interested in the system, so we triggered our multi-wavelength follow-up campaign from this point on. We initiated the next MEM observation of the system, and only 16 days later, then the X-ray flux dropped by a factor of about 300 over only 16 days. And through continued UV monitoring and X-ray monitoring, then you also see that this X-ray flux drop coincides with a UV brightening here. So this data point, and then UV brightening. And also with this continued XRT and UV monitoring, then we also see that the system undergoes cyclical behavior. And on top of this, then we also obtained radio observations of the system. And we only detect transient radio emission when the system has been in this plateau phase. So there's non-detections of the system outside of the plateau phase. Yeah. And so to go through the
in between, are those all non-detections in between the flares? Is there any quiet X-ray detected?
Yes, so the best constraints we have on the X-ray emission come from this observation here.
Yeah.
And that's just because it was deeper than all of the other ones.
And sorry, I can't tell that's a non-detection or a
oh, yeah, sorry, and these white data points are non-detection, so upper limits.
With the red star detection.
Yes, so the red star is actually a detection.
Could that be the host, or it could be, it looks like it's the AGN or NAV?
Yeah, it's not too clear. I think potentially it's just because I think it was also quite soft. So I think it's just residual disk emission at this point. But yeah, so the reason for that is when the system is X-ray faint, and the X-ray spectrum is thermal emission dominated. So it looks like the vane tail of the disk. Oops. Then as the system brightens, and you have increasing comptonization of this component. So this green spectrum here is this green data point here. And then again, increasing comptonization. And then by the time you get to each peak, then you have the X-ray emission being non-thermal emission dominated. And so this whole brightening phase potentially corresponds to formation of a corona in the system. And by the time you get to the peak of the rising phase, then you have a two temperature corona. So you have a warmer one plus a hotter component. Yeah, and so these blue squares effectively show the plateau phase. And that's when we're detecting transient radio emission, which is reminiscent apparently of the steep power law state in black hole X-ray binaries. And so like having this system means that you can track the accretion state transitions over and over again in the system. And so as Itai mentioned the other day, with QPs, they're interesting for laboratories for studying accretion processes. This system here will also be similar, because you're seeing this transition from your thermal dominated into your harder non-thermal dominated state over time. And you can also monitor like the change in the recurrence timescale over each cycle. So we've observed 5 cycles so far. And so you have a gap of about 300 days between the first and second, about 230 between the second and third, 190 and between each of the last 2. So we're not too sure about the physical interpretation for that. But I guess there's a bit of uncertainty associated with this rise here. So maybe ignore place less weight on the importance of this gap here. And yes, so the interpretation for this system is that this is a partial TDE originating in some sort of quiescent galaxy. And this is also supported by estimating the amount of mass that gets accreted in each outburst, which is about 0.17 solar masses for the first cycle, and then it decreases over each successive one. Yeah. Then on top of this, there are also 2 similar events that have been discovered over the last year. So this paper, the source that I was just talking about is on the left, and then the system AT 2018 FYK also showed a late time rebrightening. So this is a paper led by Thomas Weavers. And you see that the 2 black hole masses are fairly similar between the 2 systems. I think both were derived from the sigma relation. But you see that you have like very different recurrence timescales. And so you have 220 days in this system and about 1,200 days in 2018 FYK. And I think 2018 FYK is also undergoing the next outburst in August this year, if it's a similar system.
It actually just happened just last week.
Oh, last week, okay.
Yeah, it dropped.
And it did happen.
Yeah.
Just checking.
So I guess as well, that's a shrinking of the recurrence timescale, right? Because the initial prediction in the paper was August 2023, right?
Yeah, happened in June, 2 months sooner than that.
Yeah. So I guess there's a trend.
But Adam, so you're saying that if the orbit is shrinking by, whatever, like several.
No, I'm not saying the orbit shrink. I'm saying the recurrence timescale.
So how does that correspond to the orbit of the surviving core?
Well, it might not necessarily, because I mean, this X-ray rise. Sorry.
No, go ahead.
I was just going to say the X-ray rise is driven by the comptonization, and so it's not necessarily linked or directly correlated with the orbital period, right?
So it's not a repeating partial TDE then?
No. I think it is a repeating partial TDE, but I'm not sure whether we can cleanly link the observed recurrence timescale and the X-ray flares to.
You're saying like if you had a situation where the delay between the accretion, the new accretion and the onset lessened each time, that would also look like.
Exactly.
That might be, I could see that for like a couple cycles, but I feel like over multiple, you could calculate what sort of, how like, I don't know, it seems like that might be difficult over like 5 cycles or something. But yeah, good to look into.
So you can't tell anything about the orbit shrinking, because where I was trying to get at is, it seems like a huge amount of change in the orbital energy of that surviving star.
Yeah, that's so fast that it seems unlikely this could be a real change in orbital energy.
Over like a single orbit.
Yeah. I mean, if it hits a disk, is it possible that it would lose energy and then somehow get into a lower orbit?
Yes, but not that much energy. That's a lot of energy.
Collide with the mass. Well, it also depends on sort of the lever arm. The collision occurs at the pericenter. It would still need to collide with a very large amount of mass, which is unlikely that the star sort of intercepts that amount of mass in a single passage.
Yeah, and so to kind of go through like a rough picture of what's happening, what we think is it's effectively like the UV flaring is likely from the accretion disk, and so it's going through cycles where you're potentially getting some material stripped from the star, it's then forming the accretion disk and causing UV brightening. And when you're getting the sharp X-ray flux drop, then you have to have something to physically cause like the quantization to cut off over such a short time scale. So that's potentially linked to the star coming back in around pericenter, but we're not too sure just yet. And that would be because the UV brightening is roughly coincident with the cutoff in the X-ray corona.
What causes the corona to collapse?
That's what we're not sure about. That's what I came here for. Yeah, and then potentially you're seeing accretion state transition because the system is a relatively high black hole mass, and so the Eddington ratio of the accretion will decrease and potentially cross the boundary that you need for having these state transitions. And this is potentially explaining why you're getting the X-ray binary like cycling of the spectral properties. But yeah, we're not entirely sure what's causing the drop off in the X-ray flux. But it's one of the key things to understand for this system. Yeah. So yeah, just to summarize them. So eROSITA's detected quite a large sample of X-ray bright TDEs. Roughly, it detects about 25 strong TDEs per year, and these are X-ray selected. And most of them are optically quiet. So this will be complementary to the optically selected population. And then eROSITA's detected several repeating flares from quiescent galaxies, and they show quite a diverse set of behaviors. So yeah, thank you.
Questions? Oh, yes.
So the ratio of, repeating phenomena to straight TDEs seems sort of like 10-to-1. Is that a volume limited statement or not?
Wait, do you mean there's more repeating?
So I may have said it backwards. Yeah, the single TDE candidates are like about 10 times as many as the repeating ones, is what it looked like.
More than that, I think, right? Or the ratio.
I mean, there's also like a bias that I'll show the interesting ones in the talk.
I thought it was 25 TDEs.
Oh, for in the X-ray.
Yeah, just the
Okay.
X-ray selected
Sure.
sample.
Yes, I agree with that.
Yeah.
They seemed like similar luminosities.
Yeah, I guess we've detected 2 repeating systems at least. And then 2018 FYK was not detected by eROSITA, so we only had upper limits. Yeah, maybe 5 to 10%.
But that would be lower.
Possibly some of the Yeah, some will also repeat things.
Yeah.
Repeat
Yeah.
things.
So we don't follow up these normal TDEs at such
No, no,
late
I
times, right?
understand.
So that's the problem.
Yep.
And then on top of that, you've also got like the point that DJ mentions that TDs just don't show smooth X-ray lines. So it's very difficult to monitor systems and say this one's going to be a repeating partial TD. It's quite challenging, especially when you don't have eROSITA on.
Mhm.
Just I think Brian has a question. I'll go after Brian.
Hi, thanks for the talk. I was trying to make a connection between something you said that for the elliptical TDEs, the ones where they're already on tightly bound orbits, I guess it's true that the fallback has a finite duration. It doesn't have this tail to, you know, infinity. Were you trying to use that as a justification for why these flares were sort of, you know, of a finite duration? And this is just more of also a question to the audience. For the partial TDEs, do we expect that they would have different? Do they end up producing finite duration flares rather than power laws? I thought that they also produced sort of predictions for steeper power laws than the T to the minus 5/3. So I guess it's a question of just are your light curve shapes consistent with being partial disruptions?
Yeah, so I think I don't know where to look. Yes, so the finite accretion bursts are when the star's on a bound orbit around the black hole.
Yes, right. Which a debris, I mean, which a relic core it is, but I don't know if it's sufficiently tightly bound. Anyways, I guess my other statement is that I think it seems like this is not a criticism of you, and I think there are good reasons to think these are partial disruptions, but it does seem like that's sort of the immediate interpretation a lot of people arise at it. And one thing that Itai mentioned yesterday is that, you know, at any given time within a galactic nucleus, we may expect one of these circular emeries to exist. And it's also true that we might expect more than one to exist. So I think there can be a lot of complicated behavior between stellar emeries and other stellar emeries, some of which could produce periodic phenomena. We've looked at this as a possible QP model. And if you have two stars that are chasing each other around the black hole in a coplanar orbit, they will pass each other at intervals that can actually change considerably, even for moderate changes in the orbital separation between those two stars. So I guess my broader point is I think we should, you know, keep an open mind as to what could be producing some of these things. There could be more complicated interactions between emeries that we haven't yet modeled. Anyways, that was just a comment.
Yeah, agreed. I don't like to jump to conclusions too much for these systems because we've just seen that they show that they always surprise no matter.
Right. So an extremal version of a elliptical orbit is a circular orbit. So, anyways, thanks.
But also with emeries, do you expect them to be quite as luminous
Well, the idea would be that the two stars are they're having mass stripped off by each other. So one is passing close to another star, and there's part of its mass is stripped off by one of the stars, or a black hole in a star. You can take any two compact objects, I guess you want, and they will pass each other occasionally because each of their orbits is precessing. So eventually they run by each other if their orbits are crossing.
I guess this is really just following up what Brian said. I mean, I do think there have been some predictions in papers just based on the energetics for how short of fallback timescales you would expect based on, you can do the calculation based on the black hole mass and based on the eccentricity of the orbit for the bound degree. And so you could just look, because these are actually pretty massive, as you pointed out, pretty massive galaxies. And so that's actually more constraining because then the fallback timescale for basically zero energy orbit would be longer. And so if you're having much shorter ones and they are limited by the fallback timescale, you could put limits on when if it was a repeated TDE, what sort of orbit it would need to be in. And I think that they would probably, I mean, I need to actually do the calculation, but I would guess that the repeating timescales for TDEs would be under a year, which is maybe consistent with the shorter one, maybe not the longer one, but I think that you could do that calculation, and then if it was too, like if it just didn't make any sense, that'd be another maybe strike against repeating TD, more likely to be a QPE, but if it is more comparable, then that would be really intriguing.
I might just make this comment. I mean, it's quite trivial, but maybe worth pointing out that right, sort of in this spectrum going between full TDEs to partial TDEs, repeating TDEs, there's sort of this critical period at which something qualitatively will change, where the period of the orbiting object becomes comparable to the fallback time of the most bound debris in the zero energy case. So, if the fallback time is for a month or 60 days or something like that. So once the orbital period of this repeating object becomes shorter than that, then essentially the energy spread is all of bound material. So you won't get this late time fallback of debris that is marginally bound, simply because right, the energy spread becomes comparable to the bound orbital energy of the star. Right, so something interesting happens around this repeating phenomena on timescales of months, 100 days, 200 days. This will depend on the properties of the star and the black hole, but this is something to keep in mind regarding like qualitative transition between these two phenomena. EJ.
So, yeah, I'll make another trivial point. So irrespective of what this is, but what we're clearly seeing is a supermassive black hole going through these repeated state transitions, which has never been seen before, right? So I think these systems can be used to, study that aspect as well, irrespective of the model that you want to adopt. And people have done this for X-ray binaries since the 1990s, since XT was done. But this is the first time we get to do this for supermassive black holes and see how things evolve around it repeatedly. That's the key, right? You miss your chance, you come back and you can still do this experiment.
Yeah. And especially if we find similar systems in the future and obtain really high cadence, good quality X-ray observations of this drop, and that'll be what we potentially have chance to learn a huge amount about.
But also the M sigma is more reliable at this mass range than it is at 6, right? So that also is like a good thing.
To come back to the radio, does it correlate with the quote corona unquote?
Yeah, so I mean I think the detections are these two lines here, and also this line here. So it doesn't help having blue and black lines. Effectively, it's only ever detected when it's in the plateau stage. So something's good.
I was going to say just a quick comment. People were invoking like a stellar binary being disrupted to put something on one of these, short period orbits to give you a repeating partial disruption. If you think of just the steady state thing, I mean, there is still probably going to be some tail to, tighter binding energy, shorter periods. And there, because essentially the occupancy of the loss cone is set by the ratio of kind of the orbital time to, the kind of diffusion time in which the orbits are repopulated, you would naturally think that the more bound the orbits, the less time there is for angular momentum to diffuse, and therefore the more likely it would be a partial disruption event. So even in that kind of sample, I'm not crunching the numbers. Qualitatively, it works out.
Okay, so let's thank Adam.